Hi. So this is something I worked on the start of this year for my class on deep learning at USC. I worked in a team of 6 where we try to benchmark and analyze the current methods available to classify the EEG signals. We took up the task of classifying the EEG signals, brain EEG signals for motor movement and imagery signals to classify whether you either move or you imagine that you're moving your left arm, right arm, or the feet or your tongue. So these were the classes that the dataset had, which we used for this study. And so this study provides us kind of the optimal model, which could be used for studying EEG signals, which could potentially be used to extract features from EEG signals for the wide-ranging BCI applications that use EEG signals. So using these for prosthetics, so when you are able to detect that you are imagining a movement in your left arm, you could be using that to control prosthetics using that, as well as the models that we train on these data sets could potentially provide us transfer learning opportunities for other tasks such as epileptic seizure prediction, which was also something I worked on earlier. So trying to identify the different models available for this task, which is able to better extract these features and the pre-processing techniques and feature extraction methods available, as well as trying to perform robustness analysis by testing these models against the addition of noise, and how these models perform when we try to augment the data as well. So the robustness of the noise, it was kind of done to replicate a real-world scenario where the collection of EEG signals could potentially have some noise associated with it. All right. So the objective was, yes, to compare and benchmark the performance of the current methods. We kind of did a literature review on the models that were intended to be used for the classification of EEG signals, and the previous works on this dataset as well, and also analyze these models and methods to the addition of noise. So yeah, again, it offers insights to optimize EEG data classification as well as the feature extraction from EEG data for a wide range of BCI applications. BCI is brain-computer interfaces. So the dataset that we used for this study was the BCI Competition 42A dataset, which was EEG signals collected from 9 subjects. So there were 2 sessions on different days which were recorded for each subject. Each session was 6 runs, and each run had 48 trials, 12 trials for each of the 4 possible classes, which is either left hand, right hand, feet, or tongue, and a total of 288 trials per session. And each of these sessions included both the movement and imagery signals. The person could either be actually moving it or imagining that they are trying to move it. And the approach was to kind of explore all available pre-processing and feature extraction methods available for the EEG signals, as well as the models that have been used so far, and benchmark them and test their robustness to noise. So motor imagery tasks usually happen in the alpha and beta range of the EEG signals. Well, the pre-processing is hence a lot of frequency filtering based on the range where we want to kind of detect these motor imagery tasks, which was potentially at 4 to 38 hertz based on some studies. And then, well, feature extraction could be wavelet packet decomposition, where we kind of try to pass the discrete time signal through more filters and generate wavelet packets based on the frequency ranges within the 4 to 32 hertz or 4 to 38 hertz range that we choose. And then there's common spatial pattern, which is used in signal processing for separating a multivariate signal into additive subcomponents which have maximum difference in variance between 2 windows. I guess it's kind of like PCA, principal component analysis, where you try to find different features which have maximum variance which are orthogonal to each other. Well, yeah, and then we try to perform the robustness to noise at different noise levels. I believe we used SNR 15 and 8 decibels. So the models that we used were MLP, shallow ConNet, deep ConNet, EGNet, EG Conformer, ADCNet, and EG ITNet. I will go a bit more into the models that we used when I look at the report. But yeah, these were the models that we used. And then, yeah, this was EEG EEG Conformer. So this is kind of a preliminary presentation that we prepared that I'm going through right now. So yeah, these were some of the training curves that we obtained. So EEG was kind of one of the first models which was used to classify EEG signals specifically. And then I believe they built upon it. There was EEG V1, V2, V3, and V4. I believe that it performed decently well. I have to look at the results again. But yeah, and we also see that the deep ConNet has a decent performance. I will get to why the performance is around 60-70% here. Yeah. Alright, so this was some of the preliminary results that we had. I will get to the final results in a bit. So this was accuracy and F1 score, and then the accuracy and F1 score when we added noise. Right. So future steps could be fine-tuning the models. So we did not actually optimize the models towards this dataset itself. We kind of used a generic approach to be able to perform a comparative study rather than being able to study how the model performs itself on this dataset. So yeah, and then using other datasets could provide more insights, such as the PhysioNet EEG dataset. There were other models that we could not test, such as the hybrid ConNet and FusionNet. So that was actually one of the limitations, being able to replicate and run these large models locally on our systems and being able to benchmark them. We, due to compute limitations, we were not able to run FusionNet and FusionNet V2. And then there's more potential options for testing the robustness by potentially generating synthetic EEG data and then testing that. And then there's saliency map attack and default attack that we kind of that is also mentioned in some of the works. And then these were some of the references that we used, but it's mainly the models, different models that we try to benchmark. But yeah, let's look at the report right now. Let me get that on the screen. All right, so this was kind of the final report that we prepared for the project itself. Right, the study spans several deep learning methods. Previously published works on the task, focusing on the BCI competition for two-way dataset. We explored a range of pre-processing and feature extraction techniques. We also tested the impact of data augmentation to this dataset and tested robustness at different SNR levels. Right. So this is a bit on the dataset itself and how it was collected and the format of the dataset and some technical specifications. So 25 electrodes were used, sampling frequency, 9 subjects. Okay, so the dataset also had additional EEG channel data, which tells us whether the eyes were open, closed, or whether there were any eye movements. And some related works. And right, methodology was pre-processing with bandpass filtering, exponential moving standardization, feature extraction through common spatial patterns. We discussed that. And the window data split, Okay, so the BCI competition for two-way dataset is a pre-split dataset which had like a 50% train data and 50% test data with 9 subjects. 9 subjects each in train and test. But then to represent a more real-world scenario, we kind of made a custom split based on a subject-wise split, because we don't want to be training and testing on the same subjects. So in a real-world scenario, we're going to be testing on new patients who are not going to represent the training data set. And so yeah, that is one of the reasons that the models that we trained on potentially did not perform as well. Yeah, and again, we did not optimize these models or fine-tune the hyperparameters. But yeah, it does still provide a relative benchmark on these models. All right. So based on this customized split train and test data, we tested the different models with the different pre-processing methods as well. Right, so this is EEG-NET. So it has a temporal convolution across the time space. So it is EEG Signal is a time series data set. So there are 22 channels, I believe. and there are signal values for each of these across time. So we perform convolutions, temporal convolutions on these datasets to kind of to learn the frequency filters across time, and then followed by a depthwise convolution that applies each feature map to extract frequency-specific spatial filters. And then a separable convolution which combines a depthwise convolution and a pointwise convolution. Alright, so this structure of EEGNet allows it to kind of effectively process and interpret EEG signals by optimizing the connectivity between inputs and outputs across different convolutional stages. So basically trying to capture the temporal relationships between the signals and across channels as well. I believe that the depthwise would allow us to look across the channels. Yeah, it looks across all the 22 channels, and then these convolutions look at each of these channels. So combining all of this information provides us a better representation of what these features represent, what these signals represent. And then shallow connet, so again it has temporal convolutions followed by a spatial filter, and then just spooling to kind of reduce the dimension and a linear classification based on the number of classes that we have. And then deep con, so shallow connet had two temporal convolutions. Deep connet had four temporal convolutions, but pretty much similar. And then EEG net, well, let me quickly check if you had something more to say on that. Okay, so that was EEG conformer. So EEG conformer has CNN followed by an attention layer, convolution followed by attention, and then ADC net kind of included convolutions followed by attention as well as temporal convolutions, kind of adding on top of that. And then EEG net is a more interpretable version of these models. Right, and then let me quickly check. Also, so depthwise convolutions in these, right? So each time step is convolved across all channels, right? So that's what I said earlier. So it's across all channels to capture the spatial relation, whereas the separable convolution is proposed to compute it faster. It performs a depthwise spatial convolution followed by a pointwise convolution, which mixes together the resulting output channels. So yeah, we try to capture the relationship across channels, and then these initial temporal convolutions try to capture the temporal relationship within a channel. Perfect. And then we have data augmentation. So we try to perform some data augmentation to see how it could add on or impact our models. We utilize frequency shift as well as sign flip, shifting the frequency within a range of -2 to 2 hertz, and robustness to noise was tested at 8 decibels and 15 decibels of signal to noise ratios. Okay, so we have some results here. This is the training course again from the presentation. Alright, so we have the comparison of the final model performance from the final metrics that we obtained. These were the different models that we tested, a Conval STM. So this was something we just kind of added on with our own model. Let's see. So I believe that the EEGNet v4 did decently well. It had a 65% accuracy, and then we have so the ADC net, which kind of combines attention, temporal convolutions, and convolutions. So that performs the best here. Yes. So yeah, and then it's followed by EEGNet. All right, and then okay. So this is with augmentation, right? So we augmented the data with frequency shifting and sign flipping. So okay, we see that it has improved the performance of the ADC net as well as EEG net. There's a 66 now and a 70% now on ADC net. So these are metrics on the test data set. So the percentage increase is 4.59%. The most increase is in ADC net. And we see that it does impact negatively some models as well, such as the other models, EEGNet v1, D4 net, and EEG net. All right. And then this is a comparison of the models when noise is added. So we tested at two different noise levels, which is SNR 15, which is a mild noise level, and then some more noise with SNR 8. So the percentage drop in F1 at this level is, okay, it's pretty high with these basic models that we just added on, but these models seem to perform well. The models built for EEG signals, they're decently well. Let's see, EEG conformer, shallow FP-CSP, and I believe deep 4net and deep connet. So these four models seem to be performing well with the noise, because you can see here as well that that's 7.02, and there's the EEG conformer at 6.55 drop, and shallow FP-CSP at a 9% drop, and deep 4net, I guess this is a very good drop. Well, there is there is a bit of randomization to it because the noise added is random, but on average we could assume that it could perform similarly. But yeah, deep 4net, deep connet, EEG conformer, and shallow FP-CSP are the models that perform are the most robust to noise based on these metrics. ATC net, however, has a 10% drop and a 32% drop, and EEG net has a 4% drop here, 4.78, and a 24% drop here, which I guess is fine. But yeah, I mean, it also depends on how much allowance we want for noise, as long as the performance remains pretty good enough. But yeah, right, again, one challenge was being able to implement all these large models locally, which is why we could not implement FusionNet and Fusion V2, which seemed like a promising architecture. I've talked a bit about that as well. Extending future works could be extending the red team attacks to other distortions that could potentially affect real world data collection. And yeah, we also try to explore some other embedding techniques such as graph embedding and autoencoder to transform the raw EEG data into much more, in a compact way, be more meaningful in their representation, and provide us the features that we exactly need to look at for the classification. Alright, yeah, it could potentially be useful because EEG signals are highly dimensional, because we are collecting 22 to 25 channels from, okay, this was 25 electrodes, yeah, that's 25 channels of EEG signals over a period of time. So there's a lot of it's a high dimensional data, and it helps to be able to embed them into a smaller compact representation, which is able to provide a better feature representation. Yeah, and access to more better and higher computational resources, extending the benchmark across datasets. Alright, so yeah, this was kind of what we worked on for our course project on CSCI 566 deep learning. It was over a period of 3 to 4 months. From January to May, we started around in the middle of that, and we did our final presentation on May. So yeah, I kind of wanted to, that's kind of what we worked on, and we believe that this could potentially be used in more EEG applications, because epileptic seizure prediction is something that I would like to get back into and try to get better results with that as well. So yeah, I believe that training models on these and then using that as a transfer learning opportunity is a potential option that we could consider for that task as well. But yeah, even then we could see how we could have some insights on how which model could perform best for our task, and which model could be more robust to noise based on the collection of the data. And right, so that's what we worked on for the project, and I hope that kind of covers what we did. This report should also be available on the GitHub. I will try to link that the GitHub as well here. Alright, thank you.